Hello everyone. So we are back to our 8th chapter, D and F block elements. Now today in this lecture we will discuss the elements of the first transition series. Their name, symbol, atomic number and the outermost electron configuration, or we can say the ground state electron configuration, and then we will go for some of the general properties. Clear? Okay, so let us start. First transition series, in that the first element is scandium. Scandium symbol is Sc, atomic number is 21, and the configuration is argon 4s2 3d1. Here argon 4s2 3d1 means argon, we know that it is 1s2, then 2s2, 2p6, 3s2, 3p6. This is argon. So 18 electrons of argon. Clear? So this is called argon configuration, means 1s2, 2s2, 2p6, 3s2, 3p6. So in place of writing all these orbitals, we can simply write argon in square bracket. So argon, then 4s2 3d1. Actually we should write argon 3d1 4s2. But in whatever way you write, either argon 4s2 3d1 or argon 3d1 4s2, both are equally correct. When you write like this, then you are clear in your mind that after argon, means after 3p orbital is completely filled by 6 electrons, the next electron enters 4s orbitals and not 3d orbital. Clear? So though the 3s and 3p orbitals, they belong to the third energy level, the third orbit. Clear? But after argon, 18 electrons of argon, 19th electron of potassium and 20th electron of calcium, instead of getting added to the 3d orbital of the same energy level, the same orbit, they go to 4s orbital, because this energy level, 4s orbital, is lower in energy, and that is why it is filled up first. Clear? After 4s orbital is completely filled up, now the electron progressively enter in a 3d orbital. So scandium is having configuration argon 4s2 3d1. Clear? Then next element is titanium, Ti, atomic number 22. So configuration is argon 4s2 3d2. Vanadium, V23, it is argon 4s2 3d3. Chromium, Cr, atomic number is 24. Expected configuration after vanadium is this. Electron will progressively enter 3d orbital. So the configuration of chromium should be argon 4s2 3d4. Clear? But it is not like this. This configuration is not there for chromium. It has this configuration. Why? Because in case of transition elements, though 4s orbital is lower in energy compared to 3d orbital, but the overall energy difference between 4s and 3d is very less, and that is why electron from 4s orbital can easily be sent to 3d orbital in order to make the configuration d5. We know that d5 and d10 configurations are stable configurations. So every system has a natural tendency to achieve stability whenever possible. So here for chromium, just by sending one electron from 4s orbital to 3d orbital, it can achieve stability by having d5 configuration. So chromium is exceptional case. Its expected configuration is argon 4s2 3d4. but its actual configuration is argon 4s1 3d5. This is also important point for 1 mark or 2 marks question. Clear? So you can explain these in terms of stability. Then comes manganese. Manganese, the symbol is Mn, atomic number is 25. So if you follow this trend, then you can see the configuration is argon 4s2 3d5. Clear? So after chromium, the next electron has to enter d orbital. So this will be having d5 configuration. Clear? So manganese is having argon 4s2 3d5 configuration. Then iron, Fe, atomic number 26, configuration is argon 4s2 3d6. Cobalt, atomic number, symbol is CO, here O is small. If you write capital, then it is carbon monoxide. So C is capital, O is small. So cobalt, atomic number 27, configuration is argon 4s2 3d7. Nickel, symbol is Ni, atomic number 28, configuration argon 4s2 3d8. Copper, Cu, atomic number 29, expected configuration is argon 4s2 3d9. So after nickel, now the next electron, 29th electron of copper should enter 3d orbital. So its expected configuration is argon 4s2 3d9. But it is not so. Here again the energy difference between 4s and 3d is very less. So one electron from 4s can be easily sent to 3d orbital in order to make stable configuration argon 4s1 3d10. And this configuration is very stable as d orbitals are completely filled up. So here copper is again the exceptional case. Clear? Then comes zinc. Symbol is Zn, atomic number 30. Electron configuration is argon 4s2 3d10. So this is the expected configuration of copper. After that the next electron should go to d orbital, and so in zinc the configuration is argon 4s2 3d10. Clear? So here in this configuration you can see the electron, the last electron in all these elements enters d orbital, and that is why they are called d block elements. Clear? Now for zinc we have discussed in the previous lecture that the atom of zinc has completely filled d orbital, and Zn2+ ion, the most common ion, also has d10 configuration, and because of that reason, though zinc has the last electron present in a d orbital, it is a d block element, but it is not transition element. This we have already discussed in previous lecture. Now here we will go for copper. In copper you can see the actual configuration is d10. Now d10 means completely filled d orbital. So can copper be considered as a transition element? If we talk about copper atom, then obviously copper cannot be considered as a transition element. But in the definition of transition element we have seen that either the atom or its most common ion should contain incomplete d orbital. So here copper has two possible ions, Cu+1 and Cu+2, cuprous and cupric ions. Now let us talk about the cuprous ion, Cu+1. When Cu+1 ion is formed, then obviously this electron from 4s orbital is lost. Then also it remains 3d10. But when Cu2+ ion is formed, then one electron from 4s and one electron from 3d are lost, and so this Cu2+ ion will have d9 configuration, and out of Cu+1 and Cu+2, Cu2+ is the most common ion of copper. In most of the compounds of copper, it exists in Cu2+ form. Clear? So as in Cu2+, d orbital is incomplete, and that is why, because of this ion, copper can be considered as a transition element. So this is another important topic for 1 mark or 2 mark question, that copper, though it is having completely filled d orbital, it is considered as a transition element. Then you have to write the configuration of copper atom, means the actual configuration. Then you have to write the configuration of Cu+1 and Cu2+. Then you have to write, or you have to mention, that the most common oxidation state of copper, or the most common ion of copper, is Cu2+, and this ion is having incomplete d orbital, and that is why copper can be considered as a transition element. Clear? So this is all about one important thing, that how to remember this configuration. In this, the argon is common, 4s2 is common, exceptional chromium and copper. Clear? In that you have to write 4s1, otherwise it is 4s2 only. Then you see the atomic number of the element. Scandium 21, the last digit is 1, so in 3d 1 electron. Titanium, last digit is 2, so in 3d 2 electrons. Clear? Then vanadium, last digit is 3, so in 3d orbital there are 3 electrons. For another example, nickel, the last digit is 8, so in 3d orbital there are 8 electrons. So that is how you can remember the electron configuration of the first transition series elements. This can also be asked in 3 marks question. Once or twice it has been asked in board exam, that write name, symbol, atomic number and electron configuration of the elements of the first transition series. Very easy and scoring question in 3 marks. Clear? So you don't skip this, you have to remember, or you have to learn this well. Now let us go for general properties. In that, today we will discuss only the one property, and that is the physical property. As transition elements, they are all metals, and so they have all metallic characteristics. For example, they have high tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luster. They are very hard. Generally, metals are soft. Alkali and alkaline earth metals are soft. Non-metals are hard. But here these transition elements, they are metals, but they are very hard. They have low volatility. They have high melting and boiling point. Clear? Now what is the reason why they are so hard? Because they have more number of valence electrons. See, these are called valence electrons. The electrons present in the 4s orbital and 3d orbital, these are valence electrons. Or if you consider only 3d electrons, then also there are more number of valence electrons in in the transition elements of the first series. More is the number of electrons, more is the number of valence electrons, more bonds are formed. So more interatomic bonding is there. Clear? And that is why they are very hard. So bonding is stronger because they have more number of valence electron. Clear? Here I have written more number of valence electrons, so stronger bonding. Clear? And so they are very hard. Then high melting point and boiling point. For high melting point, what is the reason why they have high melting point? Generally metals have low melting point, but these metals have high melting point. Reason is there is involvement of n-1 d, means the electrons present in 3d orbital, and ns electrons, that is 4s electrons in case of the first transition series, in interatomic metallic bonding. Clear? So interatomic metallic bonding. See, metallic bonding is a special type of bond which is present between the metal and metal. Clear? Suppose for example we take iron. Then in iron there are many iron atoms. So they are all identical atoms. Even then there is a special type of bonding between these atoms, and this is called metallic bond. So in case of transition elements, all transition elements, not only the first series, all transition elements of 4 transition series, they have involvement of 3d means the n-1 d electrons and ns electrons in interatomic metallic bonding. So more is the involvement of the more number of valence electrons, stronger will be the bonding, and that is why they have high melting point. Here you don't have to remember the melting point which is given in the tabular form. Clear? Important is when D5 configuration is there, then melting point is highest. So in this you can see chromium and manganese, they have D5 configuration. Clear? But so here we expect highest melting point. In case of manganese, it is exception. Clear? So in the first transition series, manganese is the exceptional case, though it is having D5 configuration, but it is not having the highest melting point. Clear? Chromium is having highest. Got it? Okay. Similarly, in another transition series, the element with a D5 configuration is a technetium. Clear? TC, technetium. So this is also exceptional case. So this can be asked in MCQs. Which elements of transition series, though they have D5 configuration, but their melting points are not high. So in that, these two are the exceptional cases. Clear? Then higher boiling point, higher or very high boiling point is known as enthalpy of atomization. Clear? Now why do they have highest or very high boiling point? Reason is again more number of valence electrons, so stronger bonding. Clear? Stronger bonding with themselves as well as with the other elements. When transition elements combine with some other elements in order to form compound, then in that compound also more number of valence electrons of the transition element are involved in bonding, and so that bonding is stronger. Clear? And that is why they have higher enthalpy of atomization and higher boiling point. This enthalpy of atomization is also important factor in determining the electrode potential of this element, but that electrode potential we will study as a separate topic. Clear? So today we will discuss only the physical properties. The remaining properties like their atomic size, ionic size, then their ionization enthalpy, then their oxidation state, magnetic properties, all these properties we will take in our next lecture. So till then, goodbye, have a nice time. Thank you very much.